In Chapter 7, you're studying random variables. There are two types, discrete and continuous. As we discussed in class today, the continuous random variable that we will focus on are those from the normal distributions. So I would recommend that you go back and review information for Chapter 2 regarding those. This video will focus on what we do with the discrete probability distribution. This was a question that was posed in Parade magazine, which comes in the Sunday paper, and it was in the Ask Maryland column. My daughter is carrying triplets, gender unknown. We're trying to determine the odds of each possibility. My thinking. There are 4 possible combinations: boy, 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 girl, 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 boy, girl, girl, and girl, boy, boy, and birth order doesn't matter. So the chances are 25% for any of them, correct? Let's take a look at this situation and see whether or not David Sissel is correct in what he believes. So what is the sample space for the birth combinations? In other words, in how many possible ways could these births occur? One of the first mistakes we'll find that David is making is that birth order actually does matter. Not all babies are born at the same time. When you are having multiples, there's definitely a baby that's born first and a baby that's born second. So birth order does matter here. So if we go through and list the sample space for the birth combinations, here's what we'll have. There could be 3 boys. Or there could be 3 girls. There could be a boy, and then a girl. Or a girl, and then a boy. There could be a boy, girl, girl. Or there could be a girl, boy, boy. Or there could be a boy, girl, boy. Or girl, boy, girl. So the first thing is order does matter. And so we see here that we have 8 possible combinations. For birth order. Let's look down at question 2 to determine the likelihood of each of these combinations. Keep in mind that for any one combination, we're looking at successive events, successive births. There are 3 different trials. In any one trial, the gender of the child is considered to be equally likely. So for any one birth, whether it's the probability of boy or the probability of girl, I have the same chance, which is 1/2. And so for any combination of 3 trials, using the multiplication principle or using the idea of independent events, we could determine the combination of any one of these to be the same. So the probability of each of these events, let's take, for example, boy, boy, boy. This is like saying the probability that all 3 births are boys. So this is the probability of the first one times being a boy times the probability of the second one being a boy times the probability of the third one being a boy, which turns out to be 1/2 cubed, which is just 1/8. And we could use that for all 8 combinations. Please be careful with this. The probability is 1/8, not because we have 8 outcomes, but because each individual outcome has a probability of its own of 1/8. So now let's get to the random variable. If we let X be the number of boys that this couple could be carrying, so now if we want to find the probabilities of each of these, we just have to go back to the sample space for the possible birth combinations. I have 0 boys whenever I have all girls. That only happens in one case, and so the probability there, because girl times girl times girl, 1/2 times 1/2 times 1/2 would be 1/8. Probability of having only 1 boy, that happens when I have boy, girl, 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 boy, or girl, boy, girl. There are 3 cases where that happens. Each one has a probability of 1/8. And so if I add those together, I have 3/8. Likewise for 2, boy, boy, girl, boy, girl, boy, and girl, boy, boy. This is a probability of 3/8. And then if I have all girls, that was for 0. If I have all boys, then that only happens in one option, one combination, so that's 1/8. And then if I add all these probabilities together, I'll find that they do add up to 1. So this is a legitimate probability distribution. That answers question 3 for us. And so now we can answer David's question. We have a 12.5% chance of having no boys. We have a 37.5% chance of having one boy, a 37.5% chance of having two boys, and a 12.5% chance of having all boys. And so we can see that these events are not equally likely. I would use this as my example whenever I'm looking to make a probability distribution, and you can use it also to answer questions such as what's the probability that they'll have at least one boy, or what's the probability that they will have no more than two boys. So work with this example, try to find some different probabilities, and as always, let me know if you have questions.